So for today's pre-lecture video, I'm going to do a derivation of the continuity equation and Bernoullis equation. These are two equations that we use to study fluid dynamics. My hope is that by going over these derivations in the pre-lecture video, we might have a little bit more time in class to go over some problems and examples. So, in the second part of Chapter 12, we study fluid dynamics, which are fluids in motion. Basically, we're going to look at relationships that will help us to understand the relationship between flow speed, cross-sectional area of a pipe, and the pressure of the fluid. We'll also be able to look at situations where the flow of fluid changes height. When we're looking at fluid flow, we are going to restrict ourselves to situations where we have nice steady flow. Basically, we'll sort of imagine the fluid particles traveling in lines which aren't going to intersect with each other, and we're also going to assume that there's no really interaction with the sides of the wall and the flow lines. We're not going to really look at situations where the flow becomes turbulent. This is something a little bit more involved and complicated. The kind of flow that we're going to be looking at is what we call laminar flow. So the first thing that we're going to look at is called the continuity equation. Basically, the continuity equation helps us understand how the speed of a fluid might change if the cross-sectional area of the container changes. A good example would be something that you know from practical experience, the flow of water out of a hose. Suppose that you have a hose and you've lost the nozzle that allows you to make high pressure water come out of it. You know that by instinct, one of the things that you can do is to place your thumb over the opening of the hose. This will make the water come out faster, and it can exert more pressure on whatever you're trying to make wet or water. This is actually a good example of the continuity equation, the relationship between the speed of the flow of the fluid and the cross-sectional area. So the continuity equation is named because of the fact that it's based on the idea that the mass in equals the mass out. And when I say in and out, I'm talking about how much fluid comes in at a particular location compared to how much will come out at a different location. If we don't understand or we can't accept why these two things have to be the same, that the same amount of fluid has to go in as come out, all we have to do is think of examples where it wouldn't happen. For instance, what if more fluid came out of the second exit, out of the exit, than went in? What this means is somehow magically in between our input area and our output area, fluid was being created, which doesn't make any sense. Likewise, if we said that less fluid came out of our exit than came into the entrance, this means that somehow mass is either disappearing or being stored within our pipe. Again, this doesn't make sense. And so you can see that the continuity equation is really based on some common sense, that how much fluid goes into the pipe has to be the amount that is going to come out. And when we say that, we mean in a particular amount of time. So, using our knowledge of how we write mass for fluids, this would be equal to the density times the volume in, and that would be equal to the density times the volume out. Now, in our picture, here we see the volume of fluid coming in. And what we're doing is we're imagining the flow occurs for a certain amount of time. So we're allowing a certain time interval like dt. So during that time interval, the fluid is coming in. Now, we see that during that time dt, if the fluid started at this end and moved to the far end, the total distance that it might move we could call ds1, and that would be equal to the velocity of the fluid times the time interval. This is a simple relationship, rate times time equals distance. Similarly, at the other end, when the amount of fluid that's coming out, and if we allow that time to go, again, dt, the total distance that that fluid would have flowed in that time would be v2 times dt. So the volume of fluid that we end up having looks like a cylinder with a cross-sectional area of A1 or A2, depending on what side we're looking at, and a height of either ds1 or ds2. So let's write that. And then using our relationship that we already explained between that distance and the velocity of the fluid flow, we replace ds by the velocity times the time. Now, if we look at both sides of the expression, we see that there are some common terms, the dt and the density. So we could actually eliminate those from the expression. And what we're left with is the relationship between the cross-sectional area and the velocity. Now, one of the things I want to point out is it's a little bit difficult to deal with fluids notation-wise, at least when we're writing, because we have two different v's that we're using. The small v stands for velocity, and I'm going to try to write that in sort of a script form, while the large capital V stands for volume. In any case, you can see that the product of the area and the velocity has to remain constant. What this does is it has the effect that as area increases, velocity will go down, and vice versa. So again, here's our continuity equation. We can also state it as A times V is equal to a constant. It's kind of like a conservation law. If we look at the units, area has units of meter squared, velocity has units of meter per second. Notice then this has units of meters cubed per second, which corresponds to a volume per unit time. This is actually really basically where we started. We did say it was the mass per unit time, but this still stands, that the product of these two terms talks about the volume of fluid that flows through that pipe per unit time and says that it has to remain constant. Notice that if we take density times A times V, this is going to end up giving us the mass per unit time, which then looks a little bit more like our starting point for our expression when we were deriving it. So the other expression that we are going to look at that is important to us in terms of understanding relationships between flow is called Bernoullis equation. And Bernoullis equation allows us to add two things into the mix. It allows us to talk about the pressure that's within the pipe. And it also allows for situations where we see the height change, where the pipe might go from a lower location to a higher location. The whole basis of Bernoullis equation is really energy-based, where it's talking about the work done on the fluid and how this results in a change in kinetic energy and a change in potential energy. And so that's the basis of Bernoullis equation. The way that the work is done is through the pressure that's exerted, here again, at either end of the pipe. And so when we talk about work done by pressure, remember that force is going to be equal to pressure times area. And so here we see this. That's where the force is. And so the work will end up being the force times the distance. The work, and we'll call it just dW, is going to be force times ds, which will be the pressure times the area times ds. And we see that there's going to be work done at either end of the pipe. Let's continue with that. So the work that's done on this fluid, we have pressure exerted at either end of the pipe. Notice they're in opposite directions. We have at the left-hand side P1, A1 times DS1. And then on the other side, because the pressure is in the opposite direction, we have P2, A2, DS2. Notice that this can be simplified to P1 minus P2 times dV, because this has to be the same at both ends. Now, this work is equal to the change in the mechanical energy, as we stated earlier, which is equal to a change in kinetic energy plus a change in potential energy. The change in kinetic energy is going to be equal to 1/2 mass times V2 squared minus V1 squared. And of course, the mass can be written as 1/2 rho dV times V2 squared minus V1 squared. Notice I really tried to make the V's look different. This one is volume, these are velocities. The change in potential energy is due to the change in height of the fluid. And likewise, we can write the mass differently again in terms of density and dV. And so let's put this all together in the work expression. So for work, we have P1 minus P2 times dV. The change in kinetic energy is 1/2 rho dV, V2 squared minus V1 squared. And the change in potential energy is rho dV times G times Y2 minus Y1. One of the things we see is the dV is the same in all terms, and we can get rid of that. And then we notice we have lots of values of quantities at point 1 and point 2. And so let's gather them on like sides. And what we'll have, let's just write this one more time. P1 minus P2, getting rid of the dV. And then equating or putting all the like terms on one side. When I say like, I mean with the same subscript. And this is Bernoullis' equation. This actually allows us to look at some interesting things in terms of, what is the pressure at different locations in a pipe, given different heights or different speeds, which would be caused by different cross-sectional areas. So we can actually look at this together with the continuity equation. Basically, here's a statement of the Bernoullis equation. Basically says that the sum of all these terms together is equal to a constant. Look at the application in a particular problem here. So we have a horizontal pipe. So in this case, we're actually not going to deal with a change in height. That's okay. We could easily add that in a different problem. There's different cross-sectional areas. We know the speed at the locations, or we at least know the speed at one location, and then how it's going to change will be given by the continuity equation. And we're told that the gauge pressure at point 1 is 1.8 times 10 to the 4th pascals. I'm sorry that the superscripts and subscripts don't always translate when I go into this program, so I apologize for that. And what we want to know is, given the fact that cross-sectional area at point 2 is twice that at point 1, what is the pressure at point 2? What is the pressure in the fluid? So we can use the Bernoullis equation, but we're just going to eliminate the height term because the height at both locations is the same. Now, we know the pressure at point 1, we know the velocity at point 1. We want to find this, but we don't have the velocity at point 2 yet. But we can find that through the equation of continuity. A1 V1 is equal to A2 V2. Since we know that A2 is twice of A1, we can rearrange this to solve for V2, and it would be A1 over A2 times V1, which is going to be 1/2 of V1, because if we substitute in 2A1 here. So the velocity at point 2 is just 1.25 meters per second. We found that using the continuity equation. So let's go back to Bernoulli's equation now that we have more information. Now we know P1, we know V1, we also know this, and we can solve for P2. It just says it's water, so we'll use 1,000 for the density. And then we substitute in our values for the velocity. And the pressure that I get is 2.03 times 10 to the 4th. And so we find that the pressure here is actually higher at the thick end And if we don't understand that, we could think of how the pressures might act to either accelerate or slow down the velocity in going from one point of the point to another, pipe of the other. So because P2 is greater than P1, as the water's flowing through, it would act to slow down the water because the pressure's higher here. It would be working against it, and that would help to explain why the pressures behave as they do. I think that intuitively your expectation might be that it's the opposite way, but this actually is this way.